Hi, this presentation is about four-wheel electrical vehicle control. So as a background, current four-wheel vehicles have their steering wheel mechanically coupled to the front wheels, and power is provided by a single mechanical motor, and its power is distributed to the four wheels according to the design of the vehicle. The electrical vehicle that we are using in our project, however, provides torque for each wheel individually by a separate electric motor, and the steering wheel is mechanically decoupled from front wheels and is done electronically. The driver has three means to control the vehicle: steering wheel, gas pedal, and brake pedal, and the values of the sensors in these means are translated to longitudinal and lateral speeds of Vx and Vy and yaw rate of Rz for the vehicle. The control problem that we have in this project is to be able to achieve desired Vx, Vy, and Rz through the steering angle of the front wheels and the torques on each wheel. And the objectives that we have for this control problem is, of course, beyond stability, but on top of that, we want tracking, good tracking, so the vehicle has to be able to track these desired speeds and rates. And also we want disturbance rejection on the steering angle and modeling parameters such as mass. There are some nonlinearities in our system, but we need to take care of these nonlinearities because we are going with linear control techniques. We know we have slippage, steering, coupling between yaw motion and acceleration, and tire dynamics, which are all nonlinear in nature. In order to do that, assumptions that we made are, for example, that the vehicle has to have constant speed of Vx, or longitudinal constant speed, and we chose that speed to be 20 meters per second. That's so that the lateral forces and vehicle's general lateral acceleration can be calculated. We also assume that there's no slippage on the wheels, so that the modeling for the tires simplifies. And also we said that the change in the steering angle shouldn't be more than 6 degrees. And in general, the Vy's on each wheel, or the lateral speed, has to be small. Here is the diagram of the forces on the center of mass, Vfx, Fy, and Gz, and the component of forces on the wheels. These components are calculated using engine torque and effective radius for Fx components, and step angle and lateral stiffness for the Fy components. These components are then used together with the steering angle and the geometry of the vehicle to find the CG forces, so that later on, from those forces and the mass and the moment of inertia of the vehicle, we can find the acceleration and the vehicle speeds. Vx, Vy, and Rz in our modeling and system analysis were chosen to be our states, and A and B matrices were found according to the differential equations that we had. Interesting note is that since our output and states are the same, our C matrix is just a simple 3x3 identity matrix. This is the diagram for our modeling in MATLAB. This is the plant diagram. You can see the torques and steering as input, disturbance for later analysis, some muxing and demuxing so we can do saturation on the torque and steering angle. We have 20 degrees on both directions of saturation for steering angle and 150 Newton meter on both directions for torque. We also have both the nonlinear and linear model for comparison later, and here is their output, the state of the vehicle. We can see in our first open loop simulation that an input of 20 Newton meter of torque in all the wheels and a constant speed of 20 meters per second, which is our equilibrium longitudinal speed, causes a constant acceleration on the Vx direction while the other directions are 0. And this is perfectly making sense. And also our linear and nonlinear model are exactly the same, because we haven't deviated from our equilibrium point. As we start to deviate from our equilibrium steering angle, and add a 10 degrees of steering angle, we can see the deviation happening, but not by a lot. As we add even more deviation by adding torques so that our speed is no longer at the equilibrium point either, we can see that the deviation increases, but again, at an acceptable rate between the linear model and the nonlinear model. Then we go on with our controller design. This is a high-level sketch of our system. We have our controller, our nonlinear model of the plant, our disturbance, some initial conditions, and the desired states. For perfect tracking or good tracking, we use the tracking industrial regulator controller design, in which caused us to have 6 new states: Vx prime, Vy prime, Rz prime, and also their difference from the reference signal on each state. Notice that for perfect tracking and stability, all 6 of these states have to converge to 0. And accordingly, A and B matrices were found from the equations given for industrial regulator controllers. The augmented A and B matrices were then used in part with MATLAB pole placement command to find a K matrix for our controller. We chose the 6 negative real part poles, and we came up with different controllers. And we figured that although we are getting good tracking on all the different poles that we are trying to put in, we figured that the disturbance ejection, especially on the steering angle, is not that great. So that's what caused us to go on and try to come up with better controllers and using optimal control techniques to improve our disturbance ejection. As we know, optimal control has these weight matrices Q and R for our states and our inputs. For the states, we know that any non-zero value has high cost, because we said we want to converge to 0. So therefore, the weights associated are high, around 10,000. For our inputs, we know that torque doesn't have a lot of effect on the system, any rapid effect at least. Therefore, the relatively low costs were associated to torques, around 0.01. And for steering angle, while we know that rapid and large changes in steering angle are not practical and would make the system deviate from the equilibrium point too much, we also don't want the system to be too hesitant and reluctant on varying the steering angle. Therefore, a medium weight was given to steering angle of around 100. We then used the care command in MATLAB to calculate the K matrix, and we divided the K matrix to F1 and F2 matrices for industrial regulator design control. This is the diagram of our controller. We see the reference signals, our current states, the integrator for tracking, good tracking, F2 and F1 matrices, gain matrices, and our output, which is torque and steering angle. This is the first simulation that we did in our for our controller. We can see that we've given the system a 2 meters per second step on longitudinal speed of Vx. The behavior is good. We have 0 steady state error, 0 overshoot, and a 2.5 second 90% settling time. Our delta, Vy, and Rz are not changing, which makes sense, and we can see that the torques have saturated, which is fine, and we know that's due to the saturators that we put in our plant. Then we try to challenge the system a bit more. We put in a 10 meter per second step, and we can see that the performance has degraded. We have now 27 seconds of settling time, and our overshoot is up to 23%. And that's because of the deviation that we are having from our equilibrium speed point, which was 20 meters per second. But we can still see that the system is still stable and hasn't gone non-stable. Now, We try to challenge the system even more with a 15 meter per second step. And we can see that the system goes unstable, and it cannot converge to a stable state on all three states. So we can say that 15 meter per second is too much of a deviation from our equilibrium point on speed. Then we try to change the other inputs to our system. We input a 0.1 degree per second step to our RZ while keeping the longitudinal speed at 20 meters per second. And we can see that overshoot is 0, steady state error is 0, and we have a settling time of 31 seconds, which is high, but that's not the main purpose of our system, and Vx is much important to us. However, the system is still acting stable, and another thing to note is that Vy is going back to 0, and it's settling back to 0, which was our desired input. We can see that the delta is changing, which makes sense because we want a yaw rate, and we can also see that torques are being different on different side of the vehicle, because differential speeds are trying to accommodate for the new yaw rate. One neat effect that happened in our analysis, which is worth mentioning, is that we saw in our system that a 0.3 degrees of step to our RZ or yaw rate causes the system to saturate, because 20 degrees is the maximum angle that the steering angle can have. So the system actually saturates and can never reach the 0.3 degrees per second of yaw rate, as you can see here. So the maximum could be something around 2.5 degrees per second. Another key thing that we tried to check and was an objective for our controller was disturbance rejection. We included a disturbance of 10 degrees for around 1 second, from second 4 to second 5, while changing from 0 degrees per second to 0.1 degrees per second of yaw rate. And we saw that even though it degraded our performance a little bit by around 1 second, because the settling time increased to 32.54 seconds, the system still stayed stable, and the effect of the disturbance was negligible. We also tried to cause disturbance on some of the modeling parameters, such as mass. We increased the mass by 200 kilograms, which is around 40%, while doing a 30 meter per second step or 10 meters per second step on our longitudinal speed. And we saw that while the settling time increased to 33.82 seconds, which is increased by almost 7 seconds, the system still stayed stable, and the disturbance didn't cause instability in our system. So in conclusion, we can say that our design had very good tracking, and it also had good disturbance rejection on the steering angle and modeling parameters. We can also say that the controller was applied to a nonlinear model, and the deviations caused instability or saturation in our system. However, that was acceptable and expected, and it gave us a range of around 15 meters per second of deviation in longitudinal speed, and around 0.25 meters per second deviation in our yaw rate. And at last, we saw that optimal control actually does give us better intuition of the system, and also improves our disturbance rejection.